In our earlier video, we have already solved question 1, 2, 3. So let's solve question 4 and the remaining questions in this video. So question 4 here is showing a compound which exists as a pair of stereoisomers. Now draw a three-dimensional structure of the two stereoisomers of this compound R, and R can be used to represent the carbon chain which is given here. So if you talk about that, the R is this part and the remaining part we need to draw, and it's clearly written draw the three-dimensional structure. So we need to remember that we have to draw the dotted on the bold lines. So what is the chiral center here? The carbon here is an chiral center. So we are drawing that carbon here. Now bonded with that we have one H which is here bonded directly with the carbon, so that's the H, and the R group we are drawing here. Now we have bromine here, so bromine can be drawn in a bold line here, so we are drawing a bromine here, and then dotted line which is the remaining part, that is CH3. So CH3 is how we are going to draw the remaining part. Now let's draw the mirror image of this. That's the H here, the dotted line with CH3 here, the bold line with the bromine here, and the remaining part is R. So that's how we draw the three-dimensional structure here. Okay, done. Fine, let's go ahead with the next part. It says a sample of the same compound reacts with NaOH to make the compound shown here. So we can see that the bromine is replaced by the OH group, hydroxyl group, in an SN1 mechanism. Complete the figure 4.1 to show the mechanism of the reaction of this compound with NaOH. Include the charges, dipoles, lone pairs of electrons, curly arrows as appropriate. So we have to complete the mechanism. Now it's as mentioned, it's SN1, so only one reagent can bond with the carbon at a time. So first we need to remove the bromine, and then only the OH can bond with the carbon. So starting with the partial charges, we have to draw the partial positive and partial negative on bromine. And also we need to show a curly arrow where we can show that the bond between the carbon and bromine has to be broken. So if we draw that again, if we start, then CH3, CH2 5 times, then carbon, then H, and then CH3 as such we are drawing. Now we need to understand that the bromine has been removed. So if I draw bromine here, it has to be with a lone pair and a negative charge, because the bond which was having that electron pair is gone with the bromine, because bromine is more electronegative, so it will carry that electron pair with it. So now the carbon is fully positive, and here now we will show the nucleophile of OH minus with the lone pair and the negative charge, and we will draw a curly arrow from OH to the C positive, that is carbocation. Now we need to understand that the arrow has always to be from negative to positive. So an arrow pointing from OH, which is a nucleophile, to the positive carbon, that is carbocation. And that is how we draw, and this is how we have shown the whole mechanism here. It's completed, and such a mechanism carries 3 marks where we have to show all the partial charges, full charge on carbon, the curly arrows wherever possible, and that's how it has to be drawn. Now let's see the next part. Separate samples of this compound and the hydroxyl group also, and another of which is simple alkene, are tested with different reagents. Now understand, this is an alkene where you can see that here it's only CH and CH2, so this is an alkene. The remaining is a simple carbon chain. Here also is the same compound with the hydroxyl group, again a same compound but with the bromine on it. So keeping this in mind and the functional groups, we need to fill up the whole table. So if no reaction occurs, we need to write the cross in the relevant box. So starting with the first compound here, where we have bromine reacting with the bromine in dark, then this reaction won't occur because the bromine, elemental bromine, cannot react with the haloalkane, so there is no reaction. It can, especially when it is in dark, because that it cannot even react with the alkane chain. So then bromine, if we go to the alkene, yes, there is an addition reaction occurring where bromine will be added across the double bond. So obviously there is a reaction occurring, and so if bromine reacts, the color will change from brown to colorless. So that's how we can write the observation will be brown to colorless observation. Okay, when PCl5 reacts with the hydroxyl group, the hydroxyl group will be replaced by chlorine, but an HCl will be produced as a byproduct. So in that case, white steamy fumes will be seen. So we can write white fumes, or you can even write white or misty fumes also you can write. So this is how the observation will be seen with PCl5 with any alcohol group. Okay, then we have alkene. Alkene doesn't react with the PCl5. There won't be any addition reaction, so no reaction here. Now silver nitrate aqueous will react with any compound carrying an halogen. So here we have bromine. So with silver nitrate, the bromide compound gives a cream precipitate. So we can write cream precipitates are seen, and with hydroxyl group again the aqueous silver nitrate doesn't react. There is no reaction, so again no reaction, so cross. So let's go ahead with the next part here, D. Now again we have the same bromo compound shown here, which is heated with a reagent D to produce three different molecules E, F and G. Now we can see that E is carrying a double bond in place of the bromine. So bromine is removed and a double bond is being placed between the second and the third carbon. You can see here that the second and third carbon carries a double bond. Same in the case of F also, again second and third carbon carries a double bond, and in the compound G now there is a double bond between first and second carbon. So that shows that bromine and an hydrogen from the adjacent carbon is removed, is eliminated, and the double bond is added. So name the type of reaction. So type of reaction is elimination reaction, right? Bromine and the hydrogen from the adjacent carbon is removed to form an alkene. So that's an elimination reaction. Now the second part is identify D and the conditions used. Now D is a reagent which is used for this reaction. So for the elimination reaction, reagent used is NaOH, but not in aqueous form. Remember, if we use an aqueous NaOH, then the bromine will be replaced by the hydroxyl group to form an alcohol. Now that is not going to happen. We have an elimination reaction, so we have NaOH in the ethanol. So you can even write ethanolic NaOH. Here I am writing NaOH with ethanol, and again I will prefer adding heat and reflux. The reason being is that heat is needed definitely, but in this case reflux might not be needed as there is a long carbon chain. But any smaller chain haloalkane needs a reflux because it would be volatile compound, and any volatile compound when we heat we need a reflux. So that's the reason I'm writing reflux here, but probably the reflux might not be needed. So going ahead with the E part, both sigma and pi bonds are present in a molecule of E as a result of different types of hybridization in the carbon atom. Yes, now that is possible. Why? Because there is a double bond also. So there the two carbon carrying the double bond have a different hybridization. Okay, let's see what is the question. Complete table 4.2 to show the number of carbon atoms in each type of hybridization in a molecule of E. Now let's clarify here that any compound carrying a single bonds of all the carbon. A carbon is carrying single bonds, then it is sp3 hybridization, means a carbon have 4 single bonds, then that carbon is having an sp3 hybridization. Now if a carbon carries a double bond, then the hybridization is sp2, and if a carbon carries triple bond, then the hybridization is sp hybridization. So if we have a look at the compound E, then we have 2 carbon carrying the double bond, the second carbon and the third carbon, right? So if we talk about sp hybridization, there are no carbon carrying the triple bond. So number of carbon having sp hybridization is a 0. Now if we talk about sp2 hybridization, as I said, there should be a double bond by a carbon. So there are 2 carbon carrying the double bond, yes, so the 2 carbon have an sp2 hybridization. And if you talk about sp3 hybridization, then let's count how many carbon are having single bond. So starting with here 1, 2, 3, 4, 5 and the last one 6. So there are 6 carbon which are having single bonds, all single bonds. So that's an sp3 hybridization. So 6 carbon have sp3 hybridization. Okay, the next part is describe the essential features of an unbranched hydrocarbon that causes its molecules to show stereoisomerism. Explain how this feature leads to stereoisomerism. Now if a carbon is an unbranched, that shows there is no branch, means no optical isomerism is possible because there is no chiral center. In that case, if we say only possibility is when a carbon carries a double bond and then there is a cis trans isomerism, that is geometric isomerism. Now geometric isomerism is possible only when a carbon have a pi bond. A pi bond means you can understand that there is a sideways overlap of p orbital. Now because of that, the rotation around that carbon is limited, in the sense that the bonds around or the orbitals around the carbon cannot move that easily. So we can write that there is a limited rotation about C double bond C, that is a limited rotation. Why? The reason being is that there is a sideways overlap of p orbital and then these orbitals are difficult to rotate, and that's why there is a limited rotation. So because of that, there is a geometric isomerism seen. And how is that geometric isomerism seen? Understand, this is a 3-mark question, so you need to describe how come this limited rotation causes a stereoisomerism. So first thing is that we need a C double bond C, that is carbons carrying the pi bonds. And the second reason, the second condition required here is that the carbon should be having 2 different groups on it. Why? Because if you rotate or flip the atoms or groups around this carbon, then it should be different, then only it will show an stereoisomerism. So you can write that also there should be 2 different groups or atoms, you can write groups present on C double bond C, so on the carbon carrying the double bond. So that's why I'm writing a C with a double bond, and then only the stereoisomerism, that is geometric isomerism, is possible. So you need to write all this for getting 3 full marks, because you need to have 3 valid points to explain how geometric isomerism is possible on the compound carrying the C double bond C. So here our question 3 ends, question 4 ends. Let's go ahead with question 5. Now let's start with question 5, where it says compound W has the molecular formula C4H10O. It contains only 1 functional group. So obviously there is a functional group carrying O. Now let's see what is question 8 says. Table 5.1 shows the 2 peaks of the with the greatest M by E values in the mass spectrum of W. So W is C4H10O and there is a mass spectrum taken for this, and the M by E values given. M by E values are mass to the charge ratios, and that is 74 and 75, and the relative abundance for is 50 and X. So let's see what is the question. Calculate the relative abundance X of the peak or at m by e 75 using the information from the table 5.1. Now we can see that there is a difference of only 1, 74 and 75. So we can say that there is one of the peak is m, that is 74, and 75 is the peak of m plus 1. Now we know that the abundance of m peak is of 50, and we are supposed to calculate the abundance of m plus 1 peak, which is given x here. Now we know that the number of carbon atoms in this molecule is 4. Now we know that there is a formula for calculating the number of carbon atoms in a molecule where m and m plus 1 peak abundance are used. So that formula is 100 upon 1.1 into the abundance of m plus 1 upon the abundance of m peak. So if we substitute these, we can write as 100 upon 1.1 into abundance of m plus 1 is written here x. So let's substitute that x upon the abundance of m, that is 50, and we know that the number of carbon atom is 4, so is equal to 4. Now if we calculate the value of x, we have got is 2.2. So yes, the value of x can be written here as 2.2. Now next question. The mass spectrum of a W also shows peak at m by e value of 29 and m by e value at 59. Now suggest the molecular formulae of these fragments. Now if you talk about the fragment which is having a mass of 29 and 59, then how do I calculate this? From 29, just find out how many number of carbon atoms are possible. Now maximum number of carbon atom 2 are possible for 29, because then the mass will add up to 24 for C2. So out of 29, 24 goes for C2 carbon, so remaining is 5, so that might be for hydrogen H5. So this is the possibility of 29, and that's the only possibility, because we can't include oxygen, then the mass will go up. And if we calculate for this, yes, this is the only possibility from the formula of like C4H10O formula. Now if we talk about 59, then yes, there are 3 carbon atoms possible, because with 12 and 3, then we might have 36. Now out of 36, again we are left with the remaining mass. Again we have 1 oxygen in our molecule, so we can add up oxygen of 1 also. So C3 is 36, now plus oxygen, that is 60. That is equal to 52. So remaining from 59 we have 7. So that 7 might be for hydrogen. So 3,3H7O plus. Now why do I add plus? Because the fragments which show peak in the mass spectrometry is always a positive ions, and that's why we write m by e ratio, that is mass to the charge ratio. So this is how we get the mass fragments of 29 and 59. So the molecular formulae of these fragments are as calculated here. Okay, let's see what is the next part. A sample of WC4H10O is heated under reflux with an excess of acidified potassium dichromate until there is no further reaction. Only one organic product X is present in the mixture at the end of the reaction. Now that's not that's what we need to understand, is that there is a compound with C4H10O. It is heated under reflux with acidified potassium dichromate, that is, it is oxidized. Now potassium dichromate is an oxidizing agent, and it says it's only one product formed for which is called X from W. Okay, so that is the infrared spectrum of a W shown here. Figure 2.1 shows the infrared spectrum of W here. Okay, so this is what is shown for W, A and all that. Let's see what is the next part. Now figure 5.2 shows the infrared spectrum of X here. Okay, here is an X. Okay, there is a different infrared spectrum shown. And there is a table here showing the infrared spectroscopy absorption wavelengths for different bonds. Okay, absorption of A is shown in figure 5.1 and absorption B is shown in figure 5.2. Complete the table 5.3 using the information given in figure 5.1, 5.2 and table 5.2. Okay, table is here, yes, with the bonds and the wave numbers, absorption at which wave number. Here are the peaks of A. Yes, there is a peak of A here in figure 5.1. Okay, so we can see that A peak is approximately at 3400, okay, or maybe 3300. Yes, so let's see that what is the absorption at 32 or 33. Yes, you can see that there is an hydroxyl group between 3200 to 3650, right? So that's the absorption. We can say that. Okay, here is one more 3300 to 3500 absorption also for NH, that is amine. But yes, we know NH amine is not present in our compound. There is no N in the formula. So the only possibility which is left is for the hydroxyl group, that is the alcohol may be present. So what is the bond? OH bond might be possible. Now functional group containing the bond. Functional group containing the bond, we can write maybe an alcohol or an hydroxyl group. We can write anything. Okay, let's see what is the absorption of B. Yes, here is B in figure 5.2, which is approximately at 1700, right? So let's see what is the wave number possible at 1700. 1700 is something here. Yes, we can say 1700 is here. Fine. So that is for carbonyl or carboxyl group with the C double bond O. So what is the bond possible for B? That is C double bond O. So the functional group we can write as carbonyl, because carboxylic acid, carboxyl is not possible as we don't have two O, that is two oxygen atoms are not present, only one oxygen atom is present. So carbonyl group is present in B. Alright, so yes, let's see what's the next question. So use the information in A and B1 to draw the structure of X in the box in figure 5.3. Okay, now what I suggest that what is present in W, we have seen the mass spectrum also, and according to mass spectrum we had got two fragments of C2H5 plus and C3H7O fragment, right? So now that shows that there are 2 carbon at a time and then there are 3 carbon on one side, and that's how the fragmentation occurred, right? So C4H10O, now as we know W is an alcohol group from the information given in A, so that shows that it might be a secondary alcohol. So if we draw the structure of a W, then it should be like we have only a 4 carbon atom in our structure, so it should be like CH3, CH2, CH, CH3 and an alcohol on the second carbon atom with the secondary alcohol, because the fragmentation might occur with this CH3 the one, and yes, the second fragmentation might be of this part, right? So the fragmentation what 2 fragments we have got applies here, right? Now if it's in secondary alcohol with the formula C4H10O, and if it is oxidized with the acidified dichromate, then the secondary alcohol changes to ketone. So this is how we can draw the structure. Yes, this is how we draw the structure of a ketone, where an alcohol is in secondary alcohol with OH on the second group, so the ketone CO carbonyl group goes on the second carbon atom. Okay, let's see what's the next part. C question here. Y is a structural isomer of a W. Now both W and Y produce a colorless bubbles when sodium is added to them. Okay, Y does not react when heated with acidified potassium dichromate. Y does not react when warmed with alkaline iodine. Name the functional group present in Y. Now, if Y is a structural isomer with the same formula, both of them reacts with the sodium to give the bubbles. That shows that Y also should have an alcohol with one oxygen atom. Otherwise, there is no other functional group present which will give bubbles with the sodium with just one oxygen. Yes, carboxylic acid gives bubbles with the sodium, but then that contains two oxygen atoms, but here we have only one. So even functional group of Y should be an alcohol or hydroxyl group, right? So that's what we write here, hydroxyl group, that's the functional group. Complete the equation next to describe the reaction of W or Y with sodium, right? So C4H10O gives sodium. Now when it reacts with sodium, we know that the H of the hydroxyl group is replaced by sodium. So one of the H goes, so we will write C4H9ONA. That should be the product. And the hydrogen is released as a hydrogen gas. So now if we balance it, so that's just 1/2 here, because here only one hydrogen atom will be removed from the hydroxyl group. So we can balance it this way. So we can write here 1 and 1, or in option we can write 2, 2 and 2 here and 1 here. That is also possible, but we don't want to write that. We'll simply balance it by just putting 1, 1 and half with the hydrogen. Now draw the structure of Y. So let's see now what is the possible structure of Y. First, let's read the informations given here. Okay, we have already concluded that Y is also an alcohol just like W. But on heating with acidified dichromate, it does not react. Now, the alcohol which does not react with the acidified dichromate, that is, does not get oxidized, is only the tertiary alcohol. So Y must be an tertiary alcohol. Now, it does not react with the warmed alkaline iodine. Now, alkaline iodine is a compound which should have a secondary alcohol at this position. Now again, if this is not possible, fine, then it should be a tertiary alcohol only. So let's draw the structure of a tertiary alcohol, something like this. Yes, CH3 and yes, CH3. Yes, that is the structure possible only for Y, tertiary alcohol, where we have C4, H10 and O. Yes, this is the structure of Y. Fine, here our question paper 2 gets over. I hope my explanation is very clear and we have solved whole paper. The earlier 3 questions, first 3 questions we have solved in our earlier video, so you can watch that also.